Did you get? Is it okay now?
Yes, sir.
So actually the thing is that whenever we have our situation numerical, as we already learned from the very beginning that our mathematical operations needs to be translated into a form of equation that will involve only fundamental arithmetic and logical operation, isn't it? So at this stage, what we know that Taylor series is one of the important mathematical tools that will help us to approximate a function in the vicinity of a certain point very effectively. And that can be exploited in many of particularly for integration and differentiation. In chapter 4, we have introduced three differencing schemes during calculating the accuracy of Taylor series approximation. Can you remember, tell me what are these three differencing methods that we discussed at the time?
So Newton's divided difference method.
Yeah, the general name is Newton's divided difference. Good. But how many types of Newton divided difference were there?
The three types: forward, backward, and central.
Forward, backward, and central. Very good. You have seen that forward differences has, I am now moving, okay? For this reason, my voice might be fluctuating, okay? Please endure it. So if we have forward differences, then what you need to do, you have to take 2 points, say one is xi, another is xi plus 1. Then you need the function values at xi plus 1 and xi. Then you make the difference f xi plus 1 minus xi, then divided by xi plus 1 minus xi. Xi plus 1 minus xi, we call it the step size, isn't it?
Yes, sir.
Okay, fine. Your step size in general can be equi-spaced, but in some cases, your step size may not be spaced equally. For this reason, during integration purposes, what we have done, we have our Newton coarse formulas. In that case, trapezoidal formula is one of the most widely used one. And it is the basis of actually integration, derivation of all other integration formulas. What have we done? If we have our unequal step size, then we can apply our different types of algorithm there simultaneously in the same problem, or we can use our trapezoidal method successively or multiply to solve the same problem. Similar situation may arise in the case of differentiation. Initially, we will be considering that our data points are available with us that are equi-spaced. And you have your two classes of problem. One where your functions is not easily differentiable, but your function expressions are available with you so that you can calculate the value of your function at equi-spaced independent values. Then those discrete values can be used to calculate the differential coefficient. This is one technique. Another technique is that, say, in your laboratory, for example, you are measuring some physical parameters. Say you are measuring current and with respect to time in an inductive circuit. You try to understand what I am saying. In this way, you have to relate your mathematics to the engineering problem. For example, consider that you have your electrical circuit that contains an inductor with certain value, and a current is flowing through the inductor. You are apply. Yeah.
Sir, are you sharing anything, sir? The screen is actually in the book, sir.
No, I am not sharing anything. Just you
Oh.
try to just hear this thing. Later, I will write the thing later, because I am actually out of my seat, because I cannot sit there for 30 minutes, back pain. So what will happen? Try to just hear the thing what I am saying, not very difficult to be remembered. Then what will happen if you have a equispace point? Then that okay, you have two classes of problem. One where your function will be available, but it cannot be differentiated easily. In that case, you just discretize your independent space into equal points. Then you calculate the value of your function. Then you apply your numerical differential algorithm there to find the differential. Second class of problem is what your data itself is discrete. For example, in your laboratory, say you have an inductor, your current is flowing through the inductor, and you have connected an ammeter there to measure the current at different instance of time. Then what you will have a table. That table will have two columns. One column is your time, another column will be the current. Isn't another there?
Yes, sir.
Fine. Then if someone will call you or ask you to find the voltage across the inductor, how to find it?
L di by dt.
L di by dt, exactly. Very good. Now the question is that, can you calculate di by dt analytically? Analytical means by using mathematical expressions. Here in this problem, later problem, where you have done some experiment.
No, sir.
No, because you don't have your continuous function available to you, okay? But your answer can be a bit article. If I were you, my answer will be two. My answer can have two propositions. Number one, yes, we can use our data directly as a discrete form to calculate numerical differentiation, or we can derive an equation mathematically that will best fit the experimental data, isn't it?
Yes, sir.
Then your function with best fit curve will be available, then you differentiate it. In both ways, we can go, okay? So let us now discuss the thing from this book. Look, the thing that you have already correctly mentioned, that we have our three algorithms that we discussed earlier. One is your forward difference, another is backward difference, third one is central difference, okay, with different level of accuracy. So then if you, I am not writing, you try to see this book, this is very simple. Your equation 23.1, is it not Taylor series?
Yes, sir.
Fine. And if we solve this equation for first derivative f prime xi, you will have your equation 23.2, isn't it?
Yes, sir.
Okay. Now we, from that point ahead, we can approximate. Okay. In chapter 4, in that case, your second derivative term in equation 23.2 was discarded. A second derivative ahead, not only second derivative. Okay. Now, this is your original equation, isn't it?
Yes, sir.
Then we approximated it in this way. Okay. If we discard, for example, this region, then what will happen? We will have this equation, isn't it? This term is actually order of A. Is it not the error term or the truncation term?
Yes, sir.
Fine. Now, this is your, how many points we need? You need 2 points, xi and I.
Yes, sir.
But if we have another point xi plus 2 available with you, can't we use, for example, can't we calculate the second derivative?
Yes, sir.
By calculating the first derivative, one between xi plus 1 to xi, another between xi plus 2 to xi, then we can combine them together to find the second derivative. Can we do that?
Yes, sir.
Yes, sir.
Okay, it is there in your chapter 4. Okay. So once this is available with us, can't we add them here?
Yes, sir.
Then that will give you another version of your first derivative, isn't it?
Yes, sir. More precise.
More accurate. It will it will be more
Accurate.
where I am, because scrolling is another issue. My mouse is creating some problem. Okay, this is what that equation. Let me erase. Okay. Did not sample the equation, this one. Can you see the cursor?
Yes, sir. We can see that.
Is it not that refinement equation that this second derivative has been added?
Yes, sir.
Is it okay? Then if this second derivative is added with it, then you see that your truncation term is in the order of h square. Your h is actually very small. Of course, it is less than 1. As a result, when your error is in the order of h square, that means your error is actually what we call getting quarter after, for example, if we have our h, then
H6.
error will be 1/4, isn't it?
Yes,
Yes,
sir.
sir.
But in the case of first approximation, when our order was equal to h, you see that if your h is order of h, then if h half, then your error will, isn't it? But in the addition of your second term, it accurate, isn't it? Then after some algebra, you will find another the equation. Another version of the equation. That equation is 23.85. Okay. Now, if you want to investigate the efficacy of this algorithm, then what you need to do? You have to apply them in a problem, isn't it? Now the problem is what you can have. You have lots of problems are there in your book, but those problems are for your practice only. Okay. But in our case, what we will do? We will be applying this thing to our real problem. Okay. How to apply it? I will just, after discussing this thing, I will show this thing to you. Okay. Now, another issue is that all these things are, because we may have some, if we add for example, some further terms in it, then your accuracy will be further improved. Okay. So a version of the equations are there in table 23.1 for forward difference, 23.2 for backward difference, and 23.3 for central differences. Okay. And those are well-derived equations, so we do not have to bother about the process of derivation, but rather we have to apply them very carefully in our problem. Okay, one thing, as I have been mistakenly arrived here, but one thing I need to show to you. Okay, later. So these are your different types of algorithms. Okay. But it is very difficult to remember actually, but whenever we are doing our exam, you can have some lighter version of these equations. Okay. So here you see that the error analysis was done by using a function. This type of function we used also earlier in steps. Investigate yourself how your values are improving or how the step size is improving the error. You try to redo it. Okay. Our discussion will end with some further derivation of our derivative that is not mentioned clearly here in this book. We will take another class to finish it. For this reason, I will be showing from 23.2 in the next day. But now I will be sharing what you call whiteboard illustrating. Okay. You see in your I have given references to course outline. Are you looking through those references? Actually, the thing is that this is not something like that you are confining in one books only. So if you are confined in one book, then what will happen? Not everything will be covered there. It is your textbook. Understand, consult with other text. But very few of you are actually doing this thing, and this is probably the natural behavior. So to do, I'm discussing something from a book that is an Indian book written by, okay, name of the book is Numerical Method. Although this is a simple reproduction of an earlier book that I used in my undergraduate level. The writer is SRK Iyengar and RK Jain. Indian are very good in mathematics, but you have to choose the appropriate author. Second thing is Numerical Method. By Scarborough, one of the classical book. That book I followed in my undergraduate level. Okay, these books are available in the internet. This thing, I don't know whether you can access your library through online or not. I don't know whether the online versions of these books are available or not. Search in, at least you will find some notes based on this text. Then you can have some equations have been derived. Things are not new. Actually, what have we done? We know that if we have our n plus 1 numbers of data points, then we need a polynomial of order n so that that polynomial can go through all these data points, isn't it? So we can start with a straight line, then we can refine our approximation by using a quadratic form. Later we can use a third degree equation. Even some piecewise equations can be used. That is called interpolation that we have discussed earlier. Okay, and that will be a big topic for your class session for the exam. Can you remember your Newton Newton formula for difference formula, Newton interpolation polynomial, where we calculated two things, and a table was there. We calculated, okay, any for second order case quadratic, f2x is equal to b0 plus b1 into x minus x0 plus into minus x0 into x minus x1. Can you remember?
Yes,
This
sir.
is in article 1.2. Okay, how to find b0? If we put x equal to x0, then your b0 equal to what? B0 is
f
equal
of
to
x0.
x0, isn't it? And b1 equal to?
F of x1 minus f of
If we put
x0.
f x equal to 1, then you see that f2 into x1 minus f0, fx0, that is what is b0, divided by x1 minus x0 equal to b1, isn't it?
Yes, sir.
Okay, now tell me, is it not your what you call derivative of your function?
Yes, sir.
Yes, sir.
So in this way, what you can conclude then, you'll be related to first derivative, two is related to second derivative, and you can also have some higher order term there. And that has been generalized in article 18.1.3. I hope you have already seen it and discussed it. And later we use this thing by using a table, isn't it? We generate a data table. And then by using this table, by using the two value, this is your x, this is x0 was there, fx0 was there, fx1 was there, fx1 was there, x3, fx3 was there, isn't it? Then we use these two to find the difference, fx1 minus fx0 divided by h, isn't it?
Yes, sir.
Yes, sir.
And we again calculated the derivative here, fx2 minus fx1 divided by h. Then using these two, we calculated another derivative there.
Yes, sir.
So this is your first derivative. This is your second derivative. In this way, we can go there. Do not this thing h there, then we'll have a table. That table is simply called difference table. Using that difference table is actually containing the differences of function in multi-level. Calculate the derivative. Okay, that is the basis of the technique that I am going to discuss from now ahead. If you do not, you cannot manage this text. If you can engage clearly or effectively with this lecture, I hope you will not need. It is closed. Can you see the whiteboard?
Yes,
Yes,
sir.
sir. Can see that.
Okay, just let me drive it. So if we want to generalize this equation actually, then if fx can be written as fx is equal to say f(x0) plus x0 x minus x0 into, without b we are writing in this way, okay, del f0 divided by what, h. Similarly, you can write another term there, f(x0) into x minus x1 divided by factorial 2 into h square del 2 f0. Okay, in this way you can keep going, no problem. And this is what the generalizations of your Newton interpolation formula. Then if your data are equispaced, then we can write that a general point at any point x is equal to x0 plus s into h. You understand what is it? For example, you are dividing it in this way. This is your x0, this is your x1, this is your x2. If we can go find the what is the value of x there, you if we can if these differences are h, is it not equal to 2 x0 plus 2 into h? You understand the point?
Yes, sir.
So at any point s, for example, s, this is your xs. Then in this case, what you can do, your x value will be this, okay? X minus x0. From equation for s to what? X minus x0 divided by. This is actually the fraction of your step size. Now, as this is x, is it not also function of x? Okay. If we derivative use it, that ds divided by dx is equal to what? Is it not equal to 1 by s?
Yes, sir.
Now, if we just replace our x values, s is equal to x minus x0 divided by s, then you will see that the same equation can into this form, that your fx would be equal to fx0 plus s into del f0 plus 1 divided by factorial 2 into s minus 1 into s del 2 f 1 divided by factorial 3s into s minus 1 s minus 2 del q f0. Okay, let us stop here. Now you see that if this equation becomes the function of s, if you want to take the derivative df by dx, can you write this f divided by ds into ds dx? Can you do that?
Yes, sir.
Yes, sir.
It will be 1 divided by s df ds. Then you differentiate this function with respect to ds and write this thing. Then how to our equation will be equal to 1 by s del f0 plus half 2s minus 1 del 2f0 plus 1 divided by 6 3s square minus 6x plus 2 into del 3f0 and so on. This is very simple algebra. You can easily do that. Now, if we want to calculate the derivative, equal to x0, then you set x equal, we set x equal to x0, then s equal to what? S equal to what? Is it not equal to 0?
Yes, sir.
And if we set x equal to x1, then what will be the value of s? X1 equal to what? X1 is equal to x0 plus s, isn't it? No, x0 plus twice s or something like this. That means in this case, you will see that your s would be equal to 1. So can you write the equation by your own? By setting s equal to 0 in your equation? Yeah. Then the equation would be equal to what? If we set s equal to 0, that is we are taking the derivative at x equal, then your f prime x0 would be equal to what? 1 divided by h into del f0 minus half del 2. Okay, look, some interesting things are there. You can easily relate it with whatever thing you here. Let us stop here. Look, this is the function difference, not the differential coefficient. Okay, that means the value of your function at 2i plus 1 minus fxi divided by this difference is actually represented by del f. Okay, so this is your difference function. Now tell me, if we neglect, for example, these terms, higher order differences, then you will see that it will consider first approximation, isn't it?
Yes, sir.
Because your equation will be there 1 divided by h into del f0, isn't it? So if
Yes,
we
sir.
want to refine it at the second term, if you want to further refine it, you can add the third term. So in this way, we can calculate our derivative by using difference table. If you have your discrete data with us, okay, let me explain it with the help of an example, and that example has been taken from that book. We can use any of our practical problems. Consider that we have a table. That table contains the data x and y. Your x is 1, y equal to say 1. We have our x2, y equal to 8, x3, y equal to 27, x4, y equal to 64. This is your xy values. But we will never use these values in exam or any other purposes. We have to relate this thing with our practical problem, okay? That I have already discussed at the beginning, that if we have an inductor, we place an ammeter there to measure the current, and that inductor can have a value L. Then in this case, what will happen? Our x value is our time in second, value is our current in a, are not they?
Yes, sir.
Okay. Or even it can be a problem, something like this, that we know that by dt is equal to what?
I.
I.
I, isn't it? If your dt and dq equal to I, you see that we can use a problem. We can use many problems from our early of electrical circuit that contains this equation. And I don't know in what way you proceeded with your text in the first year. But so far, I know in the first year, I used to follow 3 or 4 books. That books actually I introduced here in this university when I started to take this course in 2000. And before that, actually, people are doing some classical something that I usually never liked. So what book you followed? Sadiku.
Yes, sir. Sadiku and a little bit of some part of Dot.
some part from DORF.
Yes.
But at one stage, using Arvind's book. Later, DORF.
That book was suggested, but we didn't go through anything of that.
We do not go through anything, but you did not go through anything, but you might be your teacher was not. But as a student to complement your learning, you experience on it. The reason is that particularly the DORF's book, you know who is DORF? Actually, DORF is one great professor in the United States. I don't know whether he is alive or not. He has written many texts for electrical engineering, not only electrical circuit. He contains some examples. Those examples are related to practical problem like the instrument that is used in medical science for treatment, like something like this. If you do not, for example, go through this book, you will understand that your tiny things are being applied in great things. Because DORF was associated with a space shuttle project of NASA. On this region, actually, when a great disaster, discovery disaster happened earlier, that I at the beginning of my course, I said to you, and probably I have shown you a website to you, that you go to your website and see many great numerical disasters, and those have been explored by the scientists, and later they figure out what are the causes. And you surprisingly know that how numerical techniques is involved there. How many of you have seen this thing? So you do not need it at this age. But I am 62, probably I will need this thing much more than this in future. For this reason, you are not giving any importance to it. How we will learn then the importance of engineering. So you see that in that book, you will find lots of examples there, particularly the fundamentals one discussed in 2 or 3 or something like this. Lots of things are there, very interesting. You will find mathematically a relationship between mathematics and engineering are there. Okay, fine. Now, if we have this equation with us, then current is available to you. Then you can easily by numerical technique. But for example, if you have given a curve, that curve is measured way. This is your current I. This is your time t in second, charge in Coulomb, and we can easily. Do you know what instrument is used to measure?
Sir, can you repeat the question again?
What type of instrument we usually use to measure charge? Have you seen it in your laboratory when it was physically accessible?
Sir, we use galvanometer to detect the presence of charge.
Presence charge, exactly. But how to measure the quantity of charge?
Ammeter.
By using ammeter.
No, sir.
Okay, try to explore it. So if we have this measurement with us, that measurement can take this value. Say at time t equal to t1, you have this Coulomb q1. For t equal to t2, you have this Coulomb q3. For t equal to t4, t3, you have another charge, say q3 there. You can form a table like this in your measurement, isn't it?
Yes, sir.
That table is available, then if you want to relate it with this problem, then your x will correspond to time in second, and your y will correspond to what? Isn't it?
Yes.
So boys, in this way, boys and girls, in this way, what you can do, you can easily relate your mathematics with all the engineering problems that you have already. Do not need any text further, for example, to proceed with the thing that are with you with your first year and second year are more than enough to understand the applications of numerical technique there. Now, What you need to do then in your charge measurement, if someone will ask you to calculate current, what you need to do? You have to calculate the derivative, right? Isn't it?
Yes, sir.
Yes.
Okay. In this case, if you want to, if someone will ask you to calculate the voltage across the inductor, you know that, but don't you know the relationship between voltage and current in an inductor? Your V
Yes,
equal
sir.
to L
L into
di
di by
dt.
dt.
So this equation and the equation I equal to dq by dt, but is there any difference between two mathematically?
No, sir.
No. So mathematician usually relate all this equation into this form, that a function f that a function say f prime x is equal to say dy by dx, something like this. They write the thing in this way, but mathematically all these things are similar. So the technique that you are using, you can readily apply to your learning that is with you, that are with learnings that are with you so far. And in future, you can also extend this thing if you can end properly. Now that if someone will ask, calculate the across the time t equal to 1 second, then what you need to do? We have to calculate the derivative of this quantity I. For example, this I derivative at t equal to 1 second, and then we have to multiply it by the value of L, isn't it?
Yes, sir.
Then we will get what? The voltage across the inductor at time t equal to 1 second. Now, in order to do that, central problem is calculate the derivative, isn't it? So if we want to calculate the derivative of t equal to 1, using this equation, by using these three terms, then what you need to do, we need to form a table that will generate this quantity del f0, 3f0, isn't it?
Yes, sir.
These are what? These are the differences of functions at the successive levels of differentiation. So if find del f0, for example, say, in our case, it will be I0, say, are not these two quantities are involved there?
Yes.
It will be equal to 8 minus 1 equal to 7. Is it okay?
Yes, sir.
Yes, sir.
If we proceed with this 2, it is 27 minus 8 is equal to 19. If we proceed with this 2, 64 minus 27 is equal to
37.
37. Is it okay?
Yes, sir.
Yes, sir.
Beautiful. Then next step is what? We have to calculate del 2 f0, isn't it?
Yes, sir.
In that case, what are the thing involved? You have to use this 2, 8 minus 7
The
equal
19
to
minus
1.
19 minus 7.
Minus 7. It is fast.
The second value is 19, sir.
বুড়া হলে মানুষ এরকম হয়, বুঝছো? এই তো এখানে আমার ধারণায় তারাই ভালো করতেছে। Because actually the thing is that are those things are very complicated actually.
No, sir.
Then 19 minus
7.
Equals to 12.
equal to
12.
then this will be equal to
37 minus 19 equals to 18.
equal to 18.
Yes.
Then can we calculate further?
Yes, sir. 18 minus 12
18
equals
minus
to
12. Cube f0.
Is it okay?
yes.
So you see the things are so easy. If you want to calculate, for example, for ft0, what you need to do, you have to traverse a path that will follow, for example, this path, isn't it? your f prime x0 is equivalently equal to, in our case, I prime and already time is over. But why you could not join at the beginning?
So we couldn't join. That meeting started at 55 most.
Sir, actually, we had the
Wrong meeting link, sir.
I paste the link in your what do you call, messenger group. Yes. And that will be equal to what? 1 divided by h. Our case h is equal to 1. Step size is equal to 1 second, isn't it?
Yes, sir.
Yes, sir.
Then our del f0 is equal to first stage del f0 equal to 7, isn't it?
Yes.
Yes, sir.
7. The second stage is equal to half into del 2 f0 equal to 12. Third stage was 1 divided by 3 into del f3 is equal to 6. So this is what the value of your integral, okay? You can easily compare the efficacy of this algorithm by adding more number, how the accuracy is increasing. But in order to measure the accuracy here in this case, you cannot apply your true criteria. The reason is that true value is actually not known to us, isn't it?
Yes, sir.
So that's it for my part today, although we have started a bit late, but inshallah in the next time we'll cover it up. Okay, you can stop recording now.